Let's start by relative motion. So, as I mentioned in the past, when you measure the position of any object, you always measure it with respect to a reference, right? With respect to a coordinate system, with respect to an observer. And if you change the observer or the reference, then you're going to get different measurements, right? I remember I mentioned about like one person from me could be 2 meters away, while from another person could be 1 meter away and in different angles. So it's always, whenever you say something about velocity, acceleration, position, and so on, you always have to mention the reference, otherwise it's meaningless. Now let's consider a case here where we are interested in measuring the position, velocity, and acceleration of a particle moving along an arbitrary path, and we call this particle B. Now, two different observers are going to measure this position, velocity, and acceleration for this particle. One of them is fixed at point O. The other one is moving itself, and we call the origin of the coordinate frame attached to this observer A. So coordinate frame x, y, z and origin O are fixed. Coordinate frame x prime, y prime, z prime with origin at A, which is attached to the moving person, it is translating. But both of these observers are measuring the position, velocity, and acceleration of the particle at B. Clearly, because one is moving, one is fixed, we don't expect them to report the same numbers, right? But we want to know how the measurements of these two people are related to each other. For example, if person A gives me the velocity of particle B, is there any way that I can tell what is the velocity of B if measured by person at O? Are these two measurements related to each other or not? Okay. So as we said, we're going to do relative measurements, relative to A, relative to O, and then connect them together. So here, the position vector of particle B with respect to observer at A, we show it with RB/A. So whenever we say B/A means B with respect to A. Then the position of particle B directly measured from observer at O, we call it R sub B. And the position of the moving observer at A as measured from O, we call it R sub A. Clearly, looking at the triangle formed here by these three position vectors, I can say that RB is equal RA plus R of B with respect to A, right? That is the triangular method for adding two vectors. So this is quite clear. If I know the position of B with respect to A, and if I know the position of A with respect to me, I can find out the position of B with respect to me by just adding them together. So position, quite straightforward, but now we can take a time derivative from the first equation and we get what? Velocity of particle B as observed by me, fixed at O, is what? The velocity that person A measures for B plus the velocity of A itself with respect to me, and another time derivatives gives the relative acceleration formula. Okay, so you see I can easily relate the measurement of particle B from A, these guys, these three, I can relate them to the measurements I make from B if I know how A itself is moving with respect to me. RA, VA, and AA. If I know them, I can easily add. Now, before I solve this a little more complicated problem, which is a star problem, problem 171, I want to first look at a simple example with you, and then we're going to get into this problem, okay? So what I do here is I'm going to look at the middle formula, the relative velocity formula with you, as I said, with a simple example. And what I do here is this example that I consider a rectilinear motion for now. So this is what I do. I consider a train. Okay, so there is a train here. And then on this train, there is a person moving. So there is a person inside this train that is moving. And then the speed of the train itself compared to an observer from the ground is, let's say, 60 meters per second to the right. And here I consider my positive x-axis to be to the right. Then there is this person, as I said, walking on the train, and the speed of walking of the person with respect to the train, it is equal to basically let's say 5 meters per second. So now if I set up a camera here from the ground, I want to know the speed of the person with respect to me. So here I'm going to use some subscripts to show some entities. So this here, the one that is fixed and it's not moving, that's the same as point O for me. Then the object of interest is this person, so this person is B. And then the one that is moving and I have a measurement with respect to is the train, and train I call it A. Okay, so it is quite self-explanatory. Now I say V of A, V of B with respect to A, and V of B. What's the meaning of them and how much is each one of these? Measuring compared to the x-axis, which is positive moving on the right hand side. So what is V of A? This A is also actually measured with respect to O. So when you say A, it's actually A with respect to what? O. And B is also with respect to O. So V of A with respect to O is what? It is the speed of the train with respect to the ground, which is 60 meters per second positive, and positive because it's to the right. Then V of B with respect to A is the speed of the person with respect to the train. Okay, so speed of the person with respect to train, and again it's to the right side, so it is going to be positive 5. Now V of B with respect to O, which is the unknown here and we have to find it, is the speed of the person as measured from the ground sensor, from the camera. So it's going to be with respect to ground, which is what we have to find out. So we use the relative velocity formula and we say V of B with respect to O is V of A with respect to O plus V of B with respect to A, and if we add them, you're going to get 65 meters per second. And it completely makes sense, right? Because the train is passing you to the right with 60 meters per second, and this person is also going faster than the train with respect to you with 5 meters to the right, so if you look at this person, his speed is the train's speed plus his own speed with respect to the wagons of the train, which is 65. Now, on the other hand, if the person was going to the left, then the difference would be this v of b with respect to a would be -5, and so here would be what? 55, right? Because he's going in the opposite direction of the train. So you see, this simple example shows you that different references would measure the speed of the same particle or object differently. Like if I had a camera here on this train, or a radar, how much would that radar measure the speed of the person? Clearly, it would measure it as 5, right? Because that camera has the same speed as the person does due to the train. So both of them are the train, so none of them would sense the motion of the train. All that this camera in purple would sense is the relative motion of the red person with respect to it, which is 5. But this green camera on the ground would sense both the motion of the train and the person with respect to the train, so it will feel 65. Okay, so they're both looking at this person, but because they are in different situations, this is fixed, that is moving, they sense different numbers. So that's the relativity of motion. Now, you might say, well, that is very easy. It's just so easy. What kind of problem can come from this topic? That could be a little bit more difficult. And I would tell you, well, there could be some problems that are a little bit more difficult than this, like this problem 13,171. So what is this problem? Let's look at this one. So here you have a boat, and on the boat you have this telltale, and this telltale would tell you the direction, as it says, of the wind relative to the boat. So it doesn't tell you how strong, what is the magnitude of the wind with respect to the boat, but it tells you which direction it is with respect to the boat. So now this boat is first sailing north at the speed v0, which is 6 nautical miles. Then in position 1, then he turns around, and in position 2, with the same speed, now he is moving to the east. And because he has changed his orientation, in the first position, the relative direction of wind with respect to boat is eastward, while here it's to the northwest at 60-degree angle with respect to the east, clockwise. Okay, so if I have this info, I want to know how much is the direction and how much is the magnitude of the wind speed with respect to the earth, not to the boat, the earth. Okay, so what is that? Because, for example, if this person wants to report the direction of the wind so that other people can use, in this position 1, he cannot say the wind is blowing from west to the east. Or in this, he can say, well, no, actually the wind is now blowing from southeast to northwest. Because they would say, well, it just took you a few seconds that you change your direction of navigation, and the wind has not changed really. How come you are reporting different directions? So what stays the same in both of these situations is the wind with respect to the ground, with respect to the earth. It has not changed. But because you change your navigation direction, each time you are measuring a different direction and probably a different magnitude. So now we have to find that. So you see, we have a lot of unknowns in this problem. All we have is the navigation direction and the relative direction of wind with respect to boat, and we have to find everything else. So let's see how we can formulate this problem. So here I'm gonna draw it. So this is boat in position 1. And it is going with the speed of v naught to the north. And here I use y to be for me corresponding to north, and I use x to be for me corresponding to east. And then here I have the boat in position 2. This time the boat is going with velocity v naught, but this time to the east. In the first situation, the relative direction of the wind is west to east. In the second situation, it is toward northwest, with this angle being 60 degrees. And that's all I have. So here, we're going to use the same notation that we used O, A, and B, and we use B to refer to the object of interest, A to refer to the moving reference, and O to refer to the fixed reference. So here, for us, O, since O was the fixed reference, for us, it means what? Earth, right? We assume here, for this small motion, that the Earth is fixed. So to us, we consider Earth to be O. A is the moving reference, which is the boat. And the object of interest is wind. So we want to know the velocity of wind with respect to Earth, and we could measure the direction of velocity of wind with respect to boat. Okay? So the problem says, what is V of boat with respect to the Earth? Both magnitude and direction. So you have to describe it as a vector, not just a magnitude only. Okay, so that is the question. And again, I would call this situation 1 or position 1, and I call this position 2. So now let's see how we can handle this problem. So we write our relative motion equation, this guy here, we write it in a vector format, not a scalar, because now my velocity is not only along one axis, it can be along both axes. So we have to write it as vectors with I and j components. So I say V of B with respect to O in position 2 is V of boat with respect to V of wind with respect to boat in position 2 plus velocity of boat with respect to the ground in position 2. Okay, and similarly I say velocity of wind with respect to the ground or earth in position 1 is velocity of wind with respect to boat in position 1 plus velocity of boat with respect to the earth in position 1. So I apply this formula that I just learned, I apply it to both situations. Now, let's see what we know about each one of these components. So what do I know about velocity of boat with respect to the ground in position 1, this guy? Clearly it is v naught, and it is in the y direction, positive y. So this guy, if I want to write it as a vector, it is going to be 6j, right? Because j is positive y, and it is v naught. Similarly, for situation 2, it is 6 units, but in the positive x direction. So this guy is going to be 6 times I, right? No big deal. Now, what do I know about the velocity of the wind with respect to boat in situation 1, this green arrow? It tells me the direction of it in the I direction, but it doesn't tell me how big it is. So what I do, I consider this vector to be the product of its magnitude. This is a magnitude. and then times its unit vector, which is positive I. Okay, so this V of B with respect to A in position 1, I don't know how big it is, but I'm sure it is in the I direction, so I write it this way. Remember, any vector is the product of its magnitude and the unit vector. And what about this situation? The velocity of wind with respect to boat in position 2. It is on this green arrow, and this green arrow has 60 degrees angle with respect to the x-axis. And so the unit vector of that, if it has a magnitude of 1, it has a cosine component in the I direction, negative, and it has a sine of 60 component in the positive j. So I don't know its magnitude, so I leave it as an unknown magnitude, V of B with respect to A in position 2. That's the magnitude I don't know. But then I multiply it by the unit vector, which is negative 1 times cosine 60, and 1 I don't need to write it, so it's negative cosine 60 times I, and then plus sine of 60 times j. Okay, magnitude times unit vector. Now, how many equations do I have here? 2 vector equations. 2 vector equations. And how many unknowns do I have? I have this magnitude I don't know. I have the other magnitude I don't know. And then this V of B with respect to O in 2 and 1 I don't know. But there is one thing I do know. I know that the V of B with respect to O in position 2 is the same as V of B with respect to O in position 1, because the direction of wind with respect to the ground has not changed. It's the position of the boat, the orientation of the boat that has changed, and so because of that, the relative wind velocity with respect to boat has changed direction. Okay, so now this is what I do. Let me write this in a better, more formal way. So I bring this down here, and as remember, we have to write nicely. I call this equation 1, I call this equation 2, and I call this equation 3. If I combine 1, 2, and 3, because their left-hand sides are equal, therefore the right-hand sides should be equal. So now I say if I use 1 and 2 and 3, I can see that the right-hand side of the first one, which is negative VB with respect to A into cosine 60I, plus VB with respect to A in position 2 sine 60J, right? That's the first component, plus 6I is equal to VB with respect to A 1I plus 6J. So the right-hand sides are equal. So I get this equality. And when 2 vectors are equal, what does it mean? Their I components should be equal on both sides, and their J components should be equal on both sides. So from one vector equality, I get 2 scalar equations. The I components equality would tell me that negative V of B with respect to A in position 2 cosine 60 plus 6 is equal to V of B with respect to A in position 1, and J equality would tell me V of B with respect to A in position 2 sine 60 is equal to 6. So from here, I can easily find V of B of BA in position 2, the magnitude, right? And sine of 60, you know, it's 1/2, so 6 divided by that is going to be 12. So this is the magnitude of the wind measured from the boat in position 2, 12. If I plug it back here and calculate the magnitude of wind with respect to boats in position 1, I should get a different number. And if you plug that 12 here by cosine of 60, which is square root 3 over 2, and add 6 to it, you're going to get 6 minus 6 square root 3. Okay? So you're going to get 6 times 1 minus square root 3, which is negative 439. And negative means it was in the opposite direction. Okay, negative does not mean the magnitude was negative. When you get a negative and you solve, you know it from statics probably, that when you solve and you end up with a negative number, it means what? It means this direction that I assumed I was not actually I, it was negative I. Okay, so it was negative 4.39 in the I, it was 4.39 in the negative I direction, not positive I. Okay? Because what's really this arrow shows me is only line of action. It doesn't show me direction. Okay? So I should actually draw something like this to be less confusing. This is the line of action of the wind. It shows it is from west to east or east to west. And in this case, it shows me from southeast to northwest. Which one? When I solve, if it's positive, it means it's in this direction. If it's negative, in this direction. So in this case, positive means that was right, but negative means it was this case. Okay, now if I plug any of these two answers, any of them, if I plug any of them back to equation 1 or 2, what do you think I would get? Yes, V of B with respect to O in 2 or 1, which should be the same thing. So I just need to plug one of these in one of the equations back. It does not matter. I can put this one back in equation 2. So here I plug this back into equation 2, and that gives me V of B with respect to O, which is 1, and that is the same as 2. It is going to be equal to negative 4319 I plus 6J meters per second. Now, the problem didn't say specified necessarily as a vector. The problem says what is the magnitude of it and what is the direction of it. Clearly, the magnitude of this is the magnitude of this vector. Which is going to be .43. By the way, I guess I made a mistake. It is not meters per second, it is knots, nautical miles. Okay, so wherever I wrote meters per second, that is wrong. It should be nautical miles, or what we call knots. And so I guess I made that mistake a few times. Good. So this is the magnitude of velocity of wind with respect to the ground, and then the direction of it, since it's negative I and positive J, right? So it looks like this. Negative I and positive J. If we want, we can measure the angle of it with respect to the north direction. And this angle is tangent inverse of 439 over 6, right? Because this guy is 439 and that is 6. So this angle theta, if we want it, it is going to be tangent inverse of 439 over 6, which is going to be, so I use A10D. Now A10, you know, in MATLAB gives you arctangents, but in radians. If you use D, it will be in degrees. 4.39 over 6, and that is 36.19. With respect to what? With respect to north and west. Right? So it is in the northwest direction with respect to the north. In the west direction, it is 36.19 degrees, and that is the magnitude, 7.43. So you see, although the problem looks very simple in the beginning, or maybe it looks, then you have to basically go through a little bit of detail to solve it. But there is nothing super complicated about relative motion.